Welcome to Data Analysis with Python. In this fifth video, the direct that is basically focused on data analysis, right? We have some videos in between that talks about um, Python, basics of Python, and of course NumPy. But when we talk about data analysis itself, this is like the fifth video in that series, and like overall, maybe 17th of 16 video. Like I think it's 17th for sure. So let's see now, the idea of exploratory data analysis. You have collected your data, you have cleaned your data, just like we saw in the last video. Now you have your data ready for exploration. So you want to check some fundamental things before you do the main analysis. That's what exploratory data analysis is about. So EDA for short, right, is the critical first step in any data project. It helps you understand the structure, trends, anomalies, and relationships in your data set before any modeling or prediction you want to do. Okay. It's also useful, of course, in anything involving data, even in data science, like you want to do machine learning and all those things, modeling data and all that. Okay, so in this case, of course, the first thing you want to do is upload your data. Of course, you can, like I said, you can create your data manually by using inbuilt Python structures like lists, dictionaries, and everything, and you convert that into a data frame like we saw previously. But here I'm trying to use external data sets. So because I know that's what a lot of people will be working with. So I've already explained in previous videos how to work with CSV files, Excel files, and of course JSON files like that. So in this video, I'll be focusing on using student scores, the data set I call student scores, which I made up myself. So I'll just show it to you. So this is it in the folder I'm working with. So you have student scores right here. So I click on it. Even in Excel, I'm not doing anything Python yet. So in this place, you have student ID as the first column. You have the name, obviously Nigerian names, and you have age, you have gender, you have grade levels, grade level. So these people are in grade level. Oh, okay. Grade level is not particularly a Nigerian thing, but it's okay. So like more like they are in what okay, well, I think it's also applicable, right? When you talk about things like basic, you have basic 1 to 9. So it's more like you have somebody, you have basic level grade 9 will be like GSS 3, grade 10 will be like SS1, and grade 11 will be like SS2, something like that. And then we'll have their math scores, their English scores, their science scores and their history score and art score. So we have 5 subjects: math, English, science, history, and art. So of course, by looking at this alone, you already have an idea what the data set looks like. All right. So then we go back to Python. All right. Okay, I'll just say don't save, right? So we'll go back to Python. All right. So, like what we've seen already, we have that CSV file. So, of course, you know how to read CSV file, like I've explained already. So, of course, this first line. Okay, let me put the line numbers for easy work. Okay, good. So, this first line is for you to import Pandas, because Pandas is the data analysis, the go-to data analysis library in Python. So without it, you can't do anything. So you import Pandas as a nickname PD. So this PD now is basically Pandas. Normally, if you did not have this PD and you just import Pandas, so you have to keep writing panda dot anything else you need from Pandas. So this read CSV is actually a function inside the Pandas library. That's why you have to, and you cannot get it on its own. That's why you have to say PD dot read CSV. That's where you can access it. Okay, so this first line, without this, it won't work. Then so in line 3 here, we upload, we convert the CSV file into a data frame. That CSV file you saw just now, you convert it into a data frame using line 3, and line 5 is where we visualize it. So if I just run it, all the three will happen at the same time. Okay. Um, so I'll just run. Of course, to run, the shortcut for running, because I want to zoom out these things, right? So I got an advice from someone to zoom out so it can be clearer. So that I want to do that. So I can use the shortcut to run without having to use without having to click on this run or this other one right? So we can just control enter. So I'll zoom this now. and I say Control Enter. So you see that star tells you it's running, and then you have it loaded like this. So you have student ID just like what you've seen. So now this is a data frame, a pandas data frame, a CSV document converted into a pandas data frame. So we can zoom this so you see everything. Of course, you have this index from pandas, then you have the student ID from the data set, you have the name. Mary Usman is the first. Ogechi Anike, Chukuma Igwe, Femi Balogun, Oluchi Kalu, Medese Henho is there, and all that. And the last name is Rukayat Ali. Okay, because you have 50 data points, so we can everything can be displayed at once. That's why this is possible. We have 50 data points numbered from 0 to 49. So we have the ages, we have the genders, we have the grade level, we have their math score, their English score, their science score, history score, and all of that. Okay, so now we have uploaded the data. Now, just like I said the other time, I'm trying to strictly keep to that now. Since I've imported pandas here, I don't have to ever worry about importing it elsewhere. It's not necessary. And once I've also uploaded, put this data frame up here, I don't have to do that again, except I have done something and I want to go back and correct and do something fresh on the original data set. So you will not see me importing and reading the CSV file like I did in previous times. I do that most of the times when I'm starting to teach people Python data analysis with Python for the first time, and they sometimes forget to import. So each cell they can then import, and then they don't have that trouble, which will delay the learning process. Okay, so now we're talking about exploratory data analysis. So you want to know what the data looks like. So by first of all seeing it this way, you already have an idea what it looks like. But then there are things Python can help you with. For instance, you can have an overview of your data set. How many rows, how many columns, what are the data types, and things like that. So and to help with this, we have info. Okay, you have info. Info provides a concise summary of the data frame, including column names, non-null count. Non-null count means uh, so values that are available. So null counts are missing values. We've talked about missing values in the previous video where we talked about data cleaning and pre-processing. So non-null counts are places where you actually have values. Null counts will be missing values. So you want to see all of that. Then you have data types, memory usage. Your data frame, that data frame we uploaded up there, this df now dot info will give you all of this information like that. So df.info will help you see what that looks like. So since I'm not going to be doing the run at the top, I'll just use the shortcut Control Enter. Okay. So from Control Enter now, you see that this particular data frame, talking about student records now, first of all, it has 50 entries. That's it. That means that you have 50 data points numbered from 0 to 49. That's you have 50 students in the class, and then the columns, you have student ID, 50 non-null. So 50 non-null all through means there's no missing data in that case. So there's no missing data. If there was missing data, you will have to do your data cleaning and all of that and pre-processing again. So here everything is intact. That's why we have 50 non-null all the way. So student ID is object, so it means you cannot carry out calculations with it, but you may categorize it, you may group it and all that. Name is also not is an object, so you can only categorize it. You cannot carry out calculations with it. Age is an integer 64, so you can carry out calculations with that. Gender is object, so you can only classify that. Then grade level is integer, math score, all the scores are integer, so you can do calculations with them. So like we said, right, you have the column names listed here. So we have 10 columns, right? Data columns, total 10 columns, numbered from 0 to 9. Then with the data types, we have all of those. And then the memory usage. So that's what you have here. So the memory usage. So that data set uses roughly 4 kilobytes, of memory space. That's what that means. So here now it tells you the data types, integer types. There are 7 of them, all these integers. And then the object types are 3. Then we don't have floats here. Floats would have been, if we have scores like 79.5, you would have had something like float in that case. So use case for info would be if you want to quickly check for missing values, or you want to identify incorrect data types, or you want to know which columns are categorical versus numerical. So you can see already that all these objects are categorical while the integers are the numerical data types. So you can see that already. So that's you getting to understand your data set that you're working with. So the next thing is you want to also know some descriptive statistics for your data. All right. And in this case, describe comes useful. So we've talked about .info. So the data frame .info gives you an overview of the rows, the columns, the data types, and all of that, and the memory usage. But here you also want a kind of descriptive statistics of the data set you have. So you use .describe, which gives count, that is the number of data points. It gives you the mean, and this only works for the numerical data types. It will only work for all these things called integer. It won't work for all the objects. So it gives you the count, the mean, the standard deviation, the minimum, the 25 percentile, 50 percentile, 75 percentile, and the maximum value. So from here you can even begin to identify outliers, if any. Okay. So here, Control Enter. So here you see it gives you a kind of statistical overview of your data set. The other one just gives you general information about columns and rows, but this gives a statistical overview, and it only works for the categorical, for the numerical data types. So that's why you see only 1, 2, 3, 4, 5, 6, 7. So those seven. So here we saw seven integer 64 type data. So those are the numerical data types. So that's what describe only. That's the only thing describe will do. Okay. So it tells you for age, for instance, all the counts are intact. We have 50, we have all the records for all the 50 students intact. Then for the age now, the average age of all the students is 15.02, right? The standard deviation of the age is 0.82. The minimum age is 14. So the youngest person in class is 14. The 25th percentile, that means that uh so a 14-year-old person is older than 25% of the class of the group we are considering. Then 50 percentile, that means that a 15-year-old person is older than 50% of the whole class. At the 75 percentile tells us that a 16-year-old person is older than 75% of the class. And of course, the maximum percentile is also 16. That means that uh, you know, the maximum age in class is 16. So the same applies to grade level. So the average grade level is 10. Of course, it's doing calculation with grade level is not really neat because it's nothing, you can't really compute with that because it's more like we're saying somebody is in SS1. So we could assign a grade level into categories, right? We could make it into categories and just say maybe ABC or something because we're not really meant to make calculations with it. So this may not make so much sense in the statistical sense of things, right? But then all these other scores now make a lot of sense. So from here you can know the highest score in maths, which is 95, the lowest score is 75. The average score across board is 84.38. Okay, we said the minimum is 75. But this looks like a very brilliant group of students. Then anybody who had 80% in maths actually is better than 25% of the class. Anybody who had 85 is better than 50% of the class. If you had 90, you're better than 95, 75% of the class. If you have 95, you are the best in class, right? That's for mathematics. So the same is applicable to other scores, as you can see. So the highest score in art, for instance, is 90. The minimum score in art is 70. The average score across board is 79. You have standard deviation and all of those things. Okay. So you can also use describe for a particular column. For instance, if we just want to see the statistical distribution for the age, so you can just say df age. You can just say df age dot describe, and you can print that, and you still get your result. Okay. So this is what this looks like. So I just press this. So it gives you just for age now. So you can also change it to say, let me just say like, I like math, right? Let me say math score. And so it gives, this is for math now. All right. So you can extract a particular column you are interested in like that. Okay. Now that's talking about describe now. We are still under descriptive statistics. So we've talked about describe. The next thing is the value counts. So you want to count the frequency of unique values. So frequency of unique ages now, if you want to count, you can do this. So you just say df age value counts. So it means there are 15 people who are 17-year-old, 17-year-old, there are 16 17-year-olds, and oh, sorry. The age, there are 17, 15-year-olds, there are 17, 16-year-olds, and there are 16, 14-year-olds, making a total of 30. So it means these are the three ages available, right? So people are either age 14, 15, or 16. So 17 are 15, 17 are 16, and 16 are 14 of years of age. So you can also do that. That's just you counting right now. What if you also want to count the people in each gender? So it means that 26 males and 24 females in class. So, you are getting an idea of what the class looks like. So you have more male than female in the class. Then what about the grade levels? There are three grade levels, 9, 10, and 11, right? So grade level 10, 17 people, grade level 11, 17, grade level 9, 16 people, like that. So so the least number of the least grade based on population is grade 9, right? So now we can also talk about mode. Mode is a talks about most frequent values. So for age now, which age values are most frequent, right? So here we have two modes, meaning that people who are age 15 and 16 are of equal proportion. I think we have seen that before. So people who are age 15 and 16 are 17 in number. So in this case now, you say that the data set is bimodal in nature. It has two modes. The age is bimodal. It is bimodal. I mean, gender wise rather. So what are we? Where am I? Yeah. Oh yeah, I'm talking about mode, sorry. So we have people who are aged 15, who are aged 16, they are the highest in number because they are equal in number and they are the highest. So it's bimodal in that sense. So what if we go for gender, male and female? So do we have more male than female? Oh, we have more male than female. So and that's clear, right? From what we saw before, 26 male, 24 female. So in terms of gender, the data set is unimodal. That is, it has one clear mode. Then for math score, uh what is the most common score? So 78, 85, and 90 are the most common, and they are the highest they are the highest number. So this will be a trimodal. This data set is trimodal in terms of math score, meaning that there's equal the highest number of people got 78, 85, and 90. Like if for instance, if everybody maybe 10 got 78, 10, if 10 is the highest number of people who scored any of these things. So you say it's tri-modal. So let's look at history. Is it unimodal? Yeah, this one is bimodal. So you have equal number of people scoring 82 and 85, right? So that's in that case, you say that's bimodal. Okay. Now, we talked about detecting outliers in the previous video. So here is just another revisit to that, although we won't be doing all the intensive way of handling outliers when we were talking about data cleaning. So, but here we have other ways of checking outliers and skewness. Skewness talks about I taught statistics on this channel. You want to check that out. I think I have about 21 videos or so under statistics or thereabouts. So I talked about skewness and kurtosis and all of those things here. So skewness just talks about where you have it's more like you have a normal distribution curve now. So if the curve is more tilted towards the left, so you say it is skewed to the left and all that. So detecting outliers and skewness. So outliers are values that lie outside the typical range. And boxplot helps to spot outliers. So by using boxplot, of course, I'm still going to talk about data visualization in the future, but now it's more like I get crashing into it because it's necessary for detecting outliers and skewness. So it's a very powerful way of you can already see from the boxplots that there are outliers or not, or there are no outliers. Okay. So if I run this now, in this case, I'll get crashing into Seaborn and Matplotlib, which we are going to be talking about when we get to data visualization. All right. So let's do that. So here we are using boxplot. By the way, Matplotlib is the primary data visualization tool in Python, and Seaborn is good for if you are doing statistical stuff. Maybe you want to show margin of error and things like that. And you cannot use Seaborn without Matplotlib. That's the interesting thing. So you can use Matplotlib on its own, but Seaborn has to depend on Matplotlib. All right. So that's the kind of idea here. So here I want to create a box plot of max scores drawn from the data frame we are working with, and the title is box plot of max score. So, and we show the plot in lines as we see in line 7, control enter. I run that. So when you see this type, it means it's running. So see that now. So what it simply tells you is that most of the scores in maths is between 80 and 90. So people who have above 90, they are like super, they are like way, they are extra, so to speak, they are like more excellent. And people who have lower than 80 are not, they are like already turning towards outliers. They're not really outliers per se, but they're like very low down there. People who have more than 90 are like really high up there. That's what this box plot just simply tells you. So this black line in between tells you the average score that people have in maths. people have an average score of 85, and most people have between 80 and 90. That's what this tells you. And then these whiskers, these other extra things. Now, they're not really outliers because we're going to see what outliers look like very soon. But they are already tending towards outliers. They are really excellent above. So these ones are like above average. These ones are like below average. Okay. But then there are really outliers that we can see when we look at other situations. All right. So let's look at this now. We want to do a box plot of age distribution according to math score or math score. Yeah, math score distribution by age rather. So we want to see for of all the ages who does better in maths according across the ages. Okay, so look at this now. You have people age 14, 15, and 16, like we saw already. Now you see that the best performers clearly are the 16-year-olds. First of all, their median score, not that I thought mean the other time it should be median. Their median score is above 87.5. And you have some really outliers tending towards 95, right? And you also have some outliers below tending towards this. So the lowest median score is from the 14-year-olds, followed by 15-year-olds, followed by 16. So as a data analyst, you're already drawing inference that, oh, okay, it looks like people have an advantage of age when it comes to as far as this data set is concerned. It looks like the older you are, the better you are at mathematics. Probably you have gained a lot of experience. You may want to infer that may not be true, but you can already begin to think along those lines, right? So you have that. So let's see another one. Let's see math score distribution by gender. Do girls do better in math than boys? That is what this is going to show us. So if you run this now, so of course the X is gender, the X axis, the Y is the math score from the data frame. So we are looking at math score distribution by gender. So according to this data set, who is better at math, boys or girls, male or female? That's what we have. Okay, interestingly, we have the higher median score is for belongs to the female. They are about 87.5 or between 87.5 and 90. So the girls are better at maths compared to the boys in this class, right? Then the median score for the boys is like 80. For the girls it's like it's 7.5. But then this is when you talk about outliers, these two dots here actually tell you that there are some very excellent boys. They don't belong to the league of these other people, right? They don't belong to this league. So you have the median score, which is 80. So most people are in that most boys, most male score between 77 around maybe 77 points, or let's even say around 78 to like 82. Most boys, their score is in that range. For girls, their score is maybe around like 87 to like 91 or something like that. All right. But then on the average, right, the girls do way better than the boys. But then you have some very excellent boys, who are out of the league of the general populace, so to speak. So according to this data set, girls are better than boys in mathematics. Okay. Then we talk about skewness. Skewness talks about symmetry. It talks about the symmetricity in the distribution of data. Like, do you have data evenly distributed? Normally, in a normal distribution, right? You have that normal distribution. So you have the left tail, you have the right tail. So if the right tail is longer, for instance, it means the data is skewed to the right. If the left tail is longer or heavier, like they say, so it means the data is skewed to the right. Like longer right tail, it means the data set is skewed to the right. Longer left tail, it means the data set is skewed to the left. That's what that is about. So it talks about asymmetry in the distribution of data. So let's say histograms. We use histogram to check skewness. Here, let's look at the age distribution and see what it looks like. Okay, this and then we can also calculate the skewness, right? So to calculate the skewness, we do the pdf.age.skew. So that helps us to calculate the skewness. Now, any skewness between 0.5 and minus 0.5 is considered to be almost symmetric, right? So this the skewness of minus 0.03 tells you that the data is fairly almost is symmetrically distributed. So if there's any skewness, we have the skewness to the left, and it's not even too noticeable like that. That's what this tells us. So let's do the same for math scores. What happens with math scores? Okay, here we have a bit more remarkable skewness to the left. So you have a longer tail to the left, for instance. So you have more people performing lower than the average score, so to speak. That's what this tells you right here. Okay, we can also do summary by category, right? We can do summary by category. So in that case, we use the group by function. Group by groups data and compute stats per category. For instance, you want to see, okay, for this age range, what is the average score among 14-year-olds? What is the average score among 15-year-olds? What's the average score among 17-year-olds? That's why here we say uh, the data frame dot group by. So we are grouping the data frame by gender and we are calculating their average age. So group by gender and calculate mean age. That's what is happening right here. So here we are grouping by age and we are we are now counting. So as we group here, we count here. So let's see what that gives us. Control enter. Okay, you see, for gender, the average age for females is 15.08. The average age for male is 14.96. So you see, the females are averagely older than the males. And we all, we saw also before, we are already beginning to draw insight from the data set, right? So we saw before that the ladies were more did better in maths than the guys, right? So, and we also saw a place where the older people did better than the younger people. So maybe we can already begin to see some insight that, oh, maybe the ladies did better than the guys because the ladies are older and they have more experience. That might be it, and that might not be. So, but those are possible explanations we can have for their performance. Now, when you come to the gender side of things, right? Okay, these are the gender counts. So we have 24 females and 26 male. So you have more males for sure. But when we talk about the age thing, so we have most females are 15. The average female is 15-year old. The average male is 14-year old. So the average female is 1 year older, or roughly. I mean, this is close, really, right? But at least we can still say that the female, an average female is older than the average male. Basically, that's what that needs to tell us. So you can begin to connect the dots here and see how beautiful data, the stories are that data can tell. So here we are grouping by gender. We are calculating their mean math score. Okay, of course, we already saw that ladies did better in math than guys. So maybe this can just buttress that idea. So here we have the average female gets 88.6 in maths, while the average male gets 80.4 in maths. We already saw something that alluded to that previously, that the ladies did better in maths than the guys, right? So we can also group by gender and calculate mean math score. So sorry, we are grouping by age, not by gender. So calculate by group by age and calculate the mean math score. So if you run that, so okay, you see who did better in maths. Age had something to do here. So 16-year-olds got an average of 85, 15-year-olds got an average of 84, 14-year-olds got an average of 82. So of course that's further buttresses what we saw the other time, that the older you are, the more likely you are at maths. The more likely you are better at maths, right? So maybe due to experience or whatever you think that might be. Okay, so we go on to talk about correlation and visualization. Correlation measures linear relationships. It shows how numerical variables relate. In Python, correlation is implemented using .corr, a short for core for short for correlation. All right, and we talk about visualizations which help in identifying trends. The dot plot function can produce scatter plots, line plots, and more. Right. Well, when we get into data visualization, we are going to see all of these things in greater detail. Right. So we talk about correlation with numerical variables. So correlation simply says that if you are good at maths, are you likely also going to be good at English? That's something, right? So, but the data will speak for itself. Now, normally, I commented this out because this correlation, this data frame dot score here, it means don't forget the data frame is that data frame we've mounted from the very beginning. So df dot core here should give us all the possible correlations. But when we get to use Seaborn under data visualization, you see that it doesn't have this challenge. So if you run this, it's going to give an error, right? So it's going to give an error. And the error is because it could not convert string to float. You remember the student ID is string. So all this S001 is not a number that you can do calculations with. That is why it has that error. And correlations is only applicable to numbers. So that is why I commented that out. But when we get to data visualization, you are going to see that what you can do a heat map without having to worry about this. So that's why that is commented, but that's a standard. If they are all numerical variables, then that challenge will happen. But then to bypass that issue, then we can now select the numerical values, right? math score, English score, science score, history score, art score. So how does score in each of these category relate with another score? So the correlation is going to give us that. So we just say from the data frame, we now have a list of lists. Okay, and now do the correlation of those. So we are correlating all the all these five groups together, and we get that result. So with Seaborn, we get like a heat map, a very nice heat map with the color grades showing you what's happening. Here we read off with the number. So you see all this 111 you're seeing, you don't worry about them because it's more. So this one is math score with math score, English score with English score. That will give us perfect correlation. So you can't really work with that. Okay, but then you can now go further and say this one now, English score with math score with English score. So the correlation between math score and English score is high, right? Because anything above 0.5 is already tending towards high, right? Then if you have anything below minus 0.5, it's already tending toward negative. You can have positive correlation. So of course, first of all, here, everything here is positive correlation. So it means everybody has a tendency of scoring higher in any other subject if they do well in a particular one. But then so others are more positively correlated than the others. I think the highest correlation, if you look around, is this 0.87, I want to believe. Yeah, this 0.87. So that there's a strong correlation between English score and art score. So it means that if a person scores high in English, they are most very likely to score high also in arts, right? Like that. Let's look at maths and science. Okay, the correlation between English score and art score is higher than the correlation between maths and science, although that's equally high too, right? So of course, basically this is telling us that we have a class of very brilliant people. I think the weakest correlation is between history and science. So it looks like history students don't really like science, or science students don't really like history. So if somebody scores high in history, they're likely going not to score as high in science. That's what this correlation tells us. So we're going to say heat maps later, which even tells the story better. Okay. So that's correlation with numerical variables. What if we want to do correlation with categorical variables? In that case, it's just all about grouping. That would amount to having a kind of cross tab. So cross tab, and that can also be very explanatory. So you want to see a number of females that are in grade 9. This is what this helps you with, and this is quite instructive too. So this simply tells us that for grade 9 students, 7 are female, 9 are male. Okay. For grade 10 students, 8 are female, 9 are male. Grade 11 students, 9 are female, 8 are male. So this also helps with a kind of level of understanding. So I could change this, right? Okay, maybe I should just copy this out, Control A, Control C, and create a new cell. Okay, I can create a new cell by just clicking on this plus. So I put this here. So instead of gender, I now have maybe I want to have a cross tab of age and gender. So I just have uh okay, let's say age and gender, whatever. Just have age right here. Then I run. Okay, so here we also have some data. So people who are aged 14, who are female 7, age 14 and male 9, age 15 and female 8, age 15 and male 9, age 16 and female 9, age 16 and male 8. Okay, then we have scatter plots. Okay, we can also scatter plots is also, well, it's a bit close. In fact, correlation values tell us a better story, but scatter plot is more like visualizing those things. So we can do a scatter plot for this, and this is what you get. So you can already see what the trend looks like. It's all over the place, but we can go further and draw like a line of best fit to show. I mean, from the look of things, right, these plots are rising. So it means on a general level, if you compare math and English score, so the higher you score in math, the higher you are going to score in English. That's what this tells us. But the correlation value tells us a better story, right? You can already pin it down that yes. History students and have higher possibility of getting scoring high also in arts. That's the idea right there. So these are for scatter plots now. So at the end of the day, let's look at we have an overview of the things you have considered. So these are all the possible things you can do as far as exploratory data analysis are concerned. Some of them overlap with data cleaning and all of that. But I mean, this is like a table that shows you all the possible things you can do as far as exploratory data analysis is concerned. So don't forget the idea is you want to have a feel of your data set that you're working with. So you get a data set for the first time. So sometimes, just like I said, data cleaning and preprocessing can overlap with exploratory data analysis, so they can go hand in hand. So I've only separated them like this for convenience, so you can follow better. But so you're going to have overlaps. So of course, you load your data. In fact, before you load your data, I always usually advise, if you have a CSV file or an Excel file, you want to open the raw file first without opening it in Python. Open it first and see. You may have to do some cleaning even on the Excel sheet itself or on the CSV file itself before you now begin to bring it to Python, because you may have issues in Python. Like I've seen data before that have maybe a question mark in some places, maybe because of some kind of errors. So I had to correct it on the Excel sheet. You can do it here too for sure, but I always advise, do whatever you can do on Excel sheet first, like naming the columns properly or whatever. But you can also do the renaming here if you like. So however you like it. So do the Excel first, do what you can do there then before you start working with Python. So I have flashed this for long, so I don't have to go run through. So you can see this and see the possibilities you have, and just implement. So I mean, this that is how it's been here. Now what I've done is, all the data code sheets, all my data sets, they are available for you to download. If you go into the description box, you can get all the data sets. Now, whatever I have done with one data set, please do with the other data sets to make you really understand the procedure. So just take the code sheet again and now take another data set. So you may have to tweak some things along the line, and that's how you really learn this thing. So let me know how helpful this video is to you, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve, or you have a data set you'd like us to work on. Feel very free. Or even if you don't have a particular data set, you just have maybe data set on something in particular, we can easily make it up, and then work with it. I'm going to work with a couple of projects by the time we are done with the core things. So you may also suggest something you'd like us to work on. If you have not subscribed to the channel, of course, you'll be missing a whole lot. So you want to subscribe right now. And if you have subscribed, be sure to hit the notification bell so you can always get alerted each time a new video is released. And for those who comment, I'm so grateful. I've learned a lot from people who comment. For instance, it didn't occur to me to zoom out, until I saw a comment like an hour or two ago. And that has really helped in making this video better. So I really appreciate that. So feel free to comment if there's something you think I need to improve on. Feel very free. I'm very open to that because I'm committed to excellence in all that I do. All right. So be sure to like and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right, just like you do maths right too. Bye.